Well, let's talk a little bit about signal conditioning using the Wheatstone bridge. Let's start by looking at how the voltage divider works. Well, the voltage divider is a circuit containing two series resistors and a voltage source. What we do with the voltage divider is that we take the output over one of the resistors. And if we look at it with the respect to that we want to take the output voltage through R2 and we start writing up some of the theory, we can say that the source voltage is the sum of all the voltage drops in the circuits. So, and with the Ohm's law we can say that the current flows through both R1 and R2, and then that the current times the sum of resistor R1 and 2 is equal to the voltage source. If we rewrite this with respect to the current, we can get that the current is equal to the voltage source divided by the sum of the resistors R1 and R2. Now, if we want to take the output voltage over R2, then we would think that there should be a current flowing in that direction too. But if we look at it and say that there is no current flowing through the output, then we can say that the voltage over resistor R2 is equal to the total current times resistor 2, which is, if we rewrite it again with respect to for the total current, then we get that the voltage drop over R2 is equal to the sum to the source voltage divided by the sum of the resistors times R2, or if we manipulate it or rewrite it again a little bit, then we get that the source voltage is times the ratio of R2 divided by the sum of R1 and R2 should give you the voltage drop over R2. We can apply the same method to get the voltage drop over R1, and we end up with an equation that says that the source voltage times the ratio of R1 divided by R1 plus R2 should give you the voltage drop over the resistor R1. So with this we have two equations to calculate voltage drop over either of these two resistors in series where we have a voltage division. We are going to use this when we look at how the Wheatstone bridge works, so keep this in mind when we are working there. Now, the Wheatstone bridge, it's a fun thing. We have in a Wheatstone bridge we have 4 resistors where there are 2 and 2 in series and in parallel with the source voltage. If we look from the source voltage, there flows the current I, which is the total current, and it comes up to the node A, where it is divided, and it goes into 2 directions. One is for I1, where it goes through a resistor R1 and R2, and the other is I2 that goes through R3 and 4. If you want to understand this better, look at the Kirchhoff's current law, where it says that the sum of all currents going into a node should be what comes out of it. Now, if we say that we want to take an output voltage between node D and B, and we say that this output voltage is equal to 0, that is, there is no current flowing between these points, then the output voltage should be 0, and we say that the bridge is in balance. And then we can say that the voltage drop AB between node A and B and the voltage drop between node A and D is the same. And if we try to write it with the Ohm's law, we can say that the current 1 times the resistor 1 is equal to the current 2 times the resistor 2. And then we can also say that that must mean that the voltage drop VBC between node B and C and VDC between node D and C is equal. And if we write it with the Ohm's law, we have that the current I1 times the resistor R2 is equal to the current I2 times the resistor R4. If we allow ourselves to divide these equations, we end up with an equation that says the ratio of resistor 1 divided by resistor 2 is equal to the ratio of resistor 3 divided by resistor 4. And this would be when the bridge is in balance. And the resistor size in itself is not important, but the ratio is. That is, that the ratio between the two has to be equal in order to the bridge, for the bridge to be in balance. Now, if we were to say that the bridge is no longer in balance, then we can say that the voltage AB and AD is not equal anymore, and we want to find the voltage drop over each. Then we would do it this way for voltage AB, which is the voltage over resistor R1. And here you can think about the voltage divider. If you go back here and look at just R2 and R1, you can see that they are in series with the voltage drop which is equal to the source voltage, so that we can allow ourselves to write it this way, where we say that the voltage AB is equal to the source voltage times the ratio of R1 divided by the sum of R2 plus R1. The same applies for the voltage drop over AD, where we end up with an equation that says the source voltage times the ratio of R3 divided by the sum of R3 plus R4. You can see this if you look at that you have R3 and 4 in series here, and the source voltage is parallel within. So looking at this, we can say that because V out is no longer in balance, we can say that the voltage drop between AD and AB should give you a difference where you have the output voltage. So we write that the output voltage is equal to voltage AB minus voltage AD. And writing this up with our previous equation for each of them, we have that the output voltage is equal to the source voltage times the ratio of R1 divided by the sum of R1 plus R2, and then minus the source voltage times the ratio of R3 divided by the sum of R3 plus R4. And with this we have an equation to find the output voltage when the bridge is not in balance anymore. That is, one of the resistors is different from the others, so that this does no longer apply where you have the ratio between them is equal. Now if we continue this, I want here to stop and play a little bit with the equation for the output voltage and find the common denominator, so that I end up with an equation that says that the output voltage is equal to the source voltage times the denominator of R4 times R1 minus multiplication of R3 and R2, and all of this divided by the denominator of the sum of R1 plus R2 times the sum of R3 plus R4. Now, if we keep this where it is and then say that we want to replace one resistor R1 by a sensor that changes its resistance when the circumstances changes, like with a temperature sensor of some kind that would change its resistance. Then we can say that instead of saying that we have R1 in the equation, now instead we write that it is R1 plus the change in R1. And we say that R1 is the initial resistance of the resistor, and theta R1 is the change in resistance. So now we write the above equation where we have this new sensor in it, where we say that we have the output voltage is equal to the source voltage times R4 times the denominator, where R4 is multiplied by the sum of R1 plus the change in R1, and minus R3 times R2. And this is divided by the denominator of the sensor resistance plus R2 times R3 plus R4. If we here remember that the bridge is in balance, and then we can say that this here applies where you say R1 times R4 minus R3 times R2 is equal to 0. And here you think, whatever you're doing here? Well, if we look back to the ratio where we said that if the bridge is in balance, then this here would apply. Where you say R1, the ratio of R1 divided by R2 is equal to the ratio of R3 divided by R4. If we manipulate this equation, then we can end up with the below equation where we say that where we say that we have R1 times R4 minus R3 times R2 is equal to 0. Knowing this, we go back to the equation where we are calculating the output voltage. And we look at the denominator where we have R4 times R1 plus R4 times the change in R1 minus R3 times R2. If we would rearrange this denominator, then you can see that a part of it is equal to the previous, where that was equal to 0, and we would only have that we have in the denominator R4 times the change in R1 for the numerator, and that means that we end up with an equation where we calculate the output voltage is equal to the source voltage times the denominator of R4 times the change in resistance R1 divided by the denominator where we have the sensor resistance plus R2 and times resistor R3 plus R4. And this only applies if the bridge is initially in balance. So if we continue with playing with this and say that if the ratio of the change of resistance R1 and R1 is much less than 1, then we can allow ourselves to manipulate the equation even further and simplify it, where we remove the change of R1 in the denominator. Look back, you can see here where you have the change of the resistance in the denominator, and here below you have removed this change so that you have simplified the equation a little bit. And this would give you a quick answer on what the initial what the output voltage would be with respect to the initial value where you have the bridge in balance. So this is about, we have talked about how the voltage divider works, so that we could use it when we were analyzing the Wheatstone bridge and find the output voltage when the bridge is not in balance. We were, for example, using a sensor instead of one of the resistors. If you want to replace more than one resistor in the bridge with sensors, then just remember to take account for that in your equation as well. So thank you very much, and continue happy working with Wheatstone Bridge.